Hi guys, welcome to our second Paleoscan tips and tricks video. For today's video, I'm going to show you how to use the Horizon Constraint tool. So this is a tool that we can use to add a previously interpreted horizon as a constraint on our model grid interpretation. So this is a very common workflow in Paleoscan. It allows us to take a previously interpreted horizon. That horizon could have come from Paleoscan itself, so it may have been extracted from a horizon stack perhaps. Otherwise, it could have been manually picked in Paleoscan, or it could have been extracted from, say, another model grid, or it may have come from an external source. It doesn't matter. As long as you have the horizon in your project, you can use the Horizon Constraint tool here to add it as a constraint on your model grid interpretation. So the only things we need to perform this process in Paleoscan are a model grid, so a model grid that's been calculated and saved into your project, and obviously the horizon or horizons that you want to use as constraints. So we can do this in batch, so we can take multiple horizons and add these as constraints to a model grid, or we can do one at a time. So these are the only things we'll need to perform this process. So once you have those objects saved into your Paleoscan project, we need to open our model grid. So the workflow that I'm going to show you today, we're going to start with the initial grid. So in Paleoscan, the initial grid is just the empty grid of nodes. So this has no prior interpretation applied onto it. That means there's no auto propagation has been applied to this. It's just the empty grid, and it's the perfect starting point for us to use the Horizon Constraint tool. Okay, so once that object is open, Paleoscan will display this little pop-up box. It's basically just saying that you have opened the initial grid, and that initial grid doesn't contain any interpretation as yet. So to obtain an interpretation, we either need to run the auto propagator. Otherwise, we can pick a horizon straight onto this initial grid, or we can add a horizon as a constraint, which is what we're going to do today. So we can hit OK. So in our model grid viewer on the left here, we have this horizon list, and in that horizon list, we have a series of unnamed horizons, all of very small area. So these are the tiny little proto-horizons or patches, and these are the building blocks of our horizons that we will be interpreting in the model grid. So initially, you'll have hundreds of thousands or millions of these little patches sitting in space. So these are the building blocks that will be used to build bigger horizons by the software, either when we run the auto propagator or when we add a horizon as a constraint. Paleoscan will use these little patches to build the bigger horizons. So what we're doing is taking a previously interpreted horizon, using the Horizon Constraint tool, and converting it to a model grid equivalent. And that model grid equivalent is comprised of these little horizon patches here. So this initial grid object is actually not the object which is opened by default when the model grid calculation completes. So when you run a model grid calculation in Paleoscan, once it's finished, Paleoscan will actually open the auto interp, which is this object here. So the auto interp is that same grid, but it's had the auto propagation applied, and therefore it has horizons interpreted. So we can see the horizon list on the left here. We now have a series of horizons. These have been interpreted by Paleoscan, and you can see they're pretty much covering the entire survey area, at least this one is. So these are horizons which have been interpreted via that auto propagation process. So this is a standard place to start for your Paleoscan interpretation, but in some cases this initial auto propagation may miss events, particularly unconformities or complex surfaces. So we can see in the northeast quadrant of this survey, we have this very obvious erosional feature, this little bevel at the top of this horse block. So something like that, particularly if it's a multipolarity event, Paleoscan will probably have a little bit of trouble picking that. So rather than just relying on the auto propagator in order to define that event, it may be worthwhile picking this type of a feature manually, and then using the Horizon Constraint tool to include that horizon in our model grid interpretation. So that's what I'm going to do today. So to perform this workflow, I generally recommend starting with the initial grid. So if you haven't already, open your initial grid. Again, we'll get this little pop-up, and the horizon list will be populated with just our little patches. So the horizon that I'm going to add as a constraint on this model grid is one that I picked manually in Paleoscan using the horizon module, which is this one here. So this might be the topic of a later tips and tricks video. So once I pick that horizon, it's been saved into my Paleoscan project in the horizon subfolder, and it's this picked horizon subfolder here. So here's the horizon I'm going to add as a constraint. So if I double click on that, we can open it in map view. And here it is. So in the northeast quadrants, you can see I've done some pretty high density picking to define this erosional feature. And I'm going to add this horizon as a constraint on my model grid. So in order to perform this process, we need to go to the model grid module, which is this one here. And about halfway along the model grid module, we have this button here, which is actually a double drop-down menu. One of the options here is horizon constraint. So if I click on this one, we will open this interface. And we have some options here for how we incorporate that horizon as a constraint on my model grid. So firstly, I need to locate the horizon I want to add as a constraint. So I'm just going to include one horizon in this case, but there's nothing stopping me adding multiple horizons here. So I've just dragged and dropped that horizon into the input box on the right, and now I have some parameters that I need to select. So the main one here that we're going to look at is this max distance parameter. So this is how far from the horizon that you're adding as a constraint that Paleoscan will look for the nearest patch or node information. So the default here is 12 milliseconds, which means Paleoscan will look 12 milliseconds above, 12 milliseconds below. If it can't find a node or a patch within 12 milliseconds, you'll have a gap. If it can find a patch within 12 milliseconds, it will use that patch as the patch that it uses to build the model grid equivalents of this horizon that we're adding as a constraint. So the polarity of this horizon is important as well. In this case, the horizon that I've picked, this unconformity here, is a multipolarity pick, which means it's covering both peaks, troughs, and zero crossings in this case. So we have this polarity option here, which allows us to specify whether the horizon we're adding as a constraint is multipolarity, which it is in this case, or a single polarity. If we choose single polarity, Paleoscan will firstly take the horizon that we're adding as a constraint here, and it will determine the dominant polarity of that surface. So perhaps I'd pick this purely on peaks or troughs. Paleoscan will assign only peak or trough polarity patches when it's trying to build the model grid equivalent of that horizon. If I choose multipolarity, Paleoscan will use any type of patch. That could be a peak, a trough, or a zero crossing, if those are included in my model grid. And it will use all the patches available to it in order to build the model grid equivalent of this horizon that I'm adding as a constraint. So these are the options we have, the parameters we can choose when we're using the horizon constraint tool. So generally, I like to drop this max distance parameter down to something a bit small, so something like 5 milliseconds or so. I prefer to have a gap rather than a jump in the horizon if possible. So I drop it down to sort of 5 or 7 milliseconds. I'd rather have a gap in the horizon, as I said, rather than have Paleoscan searching a high distance for the nearest patch, in which case I may have a jump in the horizon, which I'd prefer to avoid. So I've dropped this value down to 5 milliseconds. It's a multipolarity pick, and I'm going to hit OK. So you can see in the map view there, Paleoscan is basically scanning through the horizon and converting it to a model grid equivalent. So in my horizon list now, I have a single horizon. It has the same name of the horizon that I added as a constraint, in this case, UC 2020, etc. And the areal size of this horizon is 78 square kilometers. So you can see the previously interpreted horizon that I had was 84, so it's lost a little bit of area, but this is just part of the conversion process from a picked surface to a model grid horizon. So what I have now is I have a model grid, an empty initial grid with a single horizon included. So what I would like to do is fill in the gaps essentially. So I've started with the empty grid, I've added a horizon. What I want to do now is have Paleoscan regenerate the rest of these horizons to build me an automatic interpretation of this seismic cube. So what we can do is use this tool here, which is the automatic propagation tool. If I click on this, Paleoscan will open this little box here where I have two parameters to choose, and these are the exact same parameters that we have access to when we build the model grid initially, that being the correlation threshold, which is the similarity value that Paleoscan uses to build those horizons as part of the auto propagation process, and this thickness optimization option, which will help prevent any unlikely thickness changes in the geology, say across a fault block. So these are your two parameters that you have access to. These are the defaults. If I hit OK, Paleoscan will take the initial grid here, which includes my horizon constraint that I added, and it will perform additional auto propagation on top of that. Okay, so once that calculation finishes, which might take a little while depending on the size of your volume and the resolution of your model grid, what you should see is that you have a whole series of new horizons in your horizon list. So these are horizons which have been interpreted by Paleoscan as part of that auto propagation process. You should also see the horizon which we added as a constraint earlier. So this is the model grid equivalent of the horizon that I interpreted manually, which you can see in the top right hand corner here. And this is now included in my model grid interpretation, as well as all these other horizons which have been interpreted by the software. So the benefit of starting with the initial grid and then adding a horizon as a constraint is Paleoscan will sort of take this starting point, which is the blank grid with one single horizon in this case, and sort of use that as a framework around which it will perform the additional auto propagation. So you end up getting a better relative geological time model, at least initially, by performing this process. So I can show you that by opening the auto interp. So if I double click on this object, Paleoscan will load what we call the auto interp. So this is Paleoscan's first attempt at an automatic interpretation of this model grid. So we can see at this location here, if I toggle on the preview of the relative geological time model, so you can do that from the properties tab down here. Otherwise, you can press the T shortcut. I've got it set to the high quality preview, which you can also change from the properties. So you can see the relative geological time model at this location. It's not too bad. It's honoring the unconformity to a degree, but you can see when we toggle on the ISO line, you can really see that it's missing the geometry that I'd like to include in the model here. It's sort of punching straight through the unconformity rather than tracing along its surface. So if I do the same process, that is bring up the relative geological time model preview on my model grid with the constraint added, so this is what we were just looking at, we'll be able to see how adding the constraint has impacted the automatic interpretation here. So you can see the ISO line at that exact same location is now hitting that unconformable surface and tracing it along its length. So this is much closer to a geologically realistic scenario in this particular case. And the way that we got to this is by starting with the initial grid, adding a horizon as a constraint, and then running the automatic propagation. So just make sure you save your interpretation once that calculation is finished. That will then save a new interpretation alongside your model grid, which here I've called interp constraint. And that will then be your starting point upon which you can perform additional horizon interpretation in your standard Paleoscan model grid interpretation workflow. So that's it for this tips and tricks video. If you'd like more information on this horizon constraint tool, you can access the Paleoscan user guide by pressing F1, and you can see more information on that horizon constraint tool on page 236. Thanks for watching the tips and tricks video, guys. If you have any requests for topics that you'd like to see covered in the next tips and tricks video, then feel free to write those in the comments. Otherwise, I'll see you in the next tips and tricks video next week. Thank you.